Good morning. Exploring the Solar System Part 6. This is the sixth and I think final episode of the Exploring the Solar System trilogy. And this is about the origin of the solar system. So I'll be saying a little bit about how it formed, what clues we have as to how we know how it formed, and basically what simulations are telling us, and a few of the questions that are trying to be resolved. So when you build a model of the solar system, an orrery, like this brass orrery there, it's built from the inside out. You start with the sun and then you add the planets. You add Mercury, then you add Venus, and then you add the Earth, etc. But that's fine for an orrery, but that's not how the solar system was actually made. When we look out into the Milky Way, we see lots of these clouds of hydrogen and a few other elements mixed in. This is one of the closest star-forming regions in our Milky Way. It's only about 400 light-years away, and it's a star system called Rho-Ophiuchi. And this cloud complex, we know, is forming stars. Hundreds of new stars are forming within this cloud, and we think there's enough mass in a cloud like this to actually form thousands of clouds. And we are fairly sure that our sun and our planets formed from a cloud that's rather similar to this one. As you can see from the scale, these clouds are typically many, many light years in size before they finally collapse into individual star systems. So to try and get a handle on how this works, I've tried to put things on a sort of timeline. You can see here a timeline ranging from the first few 100,000 years through various millions of years, and we are now at 4.6 billion years after the sun originally formed on the right-hand side. But most of the action is taking place in these first few million or tens of millions or hundreds of millions of years. So what happened very early on was this cloud, not necessarily looking exactly like this one, but just representative. A cloud collapsed, and as it gravitationally collapsed, various parts of the cloud warmed up and formed what we call a T-Tauri system. This is simply the name of a star that gives the name for this particular type of early star formation. So it took a few million years for the cloud to collapse and heat up to the point where we're starting to develop a star. And around that star, a whole load of gas and dust is also circulating. Fusion didn't actually start until about 30 million years or so. In other words, the star was not nuclear powered until quite some time after the start of the star's history. So at that point, this Hertzsprung-Russell diagram at the bottom here is a diagram of luminosity on the vertical scale and surface temperature on the horizontal scale. So after about 30 million years or so, that's when the star actually switched on and had a nuclear furnace which was starting to which was then starting to power the star. And we think the sun was actually born in a cluster, given that the cloud that produced it was enough to certainly produce hundreds, if not thousands of stars. Then, Teams has interrupted again. So we know that the system created a cluster of stars, and so the sun was probably born with hundreds, if not thousands, of siblings. But after something of order hundreds of millions of years, the cluster would drift apart and leave the sun on its own. So in the early stages, leading up to about 10 million years or so, the proto-star, the early star, was surrounded by a whole load of gas and dust, which didn't clear until something like 10 million years or so after the formation of the star. So that's, roughly speaking, the timeline of how the sun came to be and how the sun switched on. Now we know that stellar systems can quite often have gas and dust around them. For instance, within this particular cloud, the Hubble Space Telescope has looked in detail at a number of stars that are being born in there. And for instance, the image in the bottom right shows a star system that's surrounded by a disk of gas and dust. The star itself in this image is obscured because it's so dusty, visible light finds it very difficult to get out, and visible light is scattered. So we do see visible light scattered off part of the dust around the star. We don't see the star itself. And we know that this is fairly common, this idea of a whole load of gas and dust around the star, a so-called protoplanetary disk, a disk that ultimately will make the planetary system in the solar system. We know this is fairly common because we've seen protoplanetary disks around a lot of other stars. It's not so easy to see these in visible light because they're relatively low temperature. It's much easier to see them in infrared or in the millimeter wavelengths. And when we look at other stars, we now have hundreds of different star systems, all of which are showing protoplanetary disks around them. So we know that this is not an uncommon scenario. This particular set of data was taken with a millimeter wavelength telescope, the so-called ALMA, the Atacama Large Millimeter Array, a whole collection of telescopes in the Atacama Desert, all working at wavelengths of order millimeter, where we're getting relatively cool systems, not the star itself, but the protoplanetary disk around the star. And we think what's actually happening is we start with a star in the middle and a whole load of gas and dust in a protoplanetary disk around it, and that dust starts off nanometer or micron size and slowly will accrete to dust grains and then into pebbles and then into bodies which tend to be called planetesimals and protoplanets on their way to being planets. On the right-hand side there's just a reminder of the size of the Earth and Jupiter on this scale that ranges from nanometers on the left to gigameters on the right. So down at this left-hand end, the grains, there are grains of carbon materials, silicon materials in the interstellar medium, and that will be mixed into this protoplanet disk surrounding our sun. Those tiny little grains will stick together when they bump into other grains, and there are so many of them, then we will find that we have a whole load of the video is looking a bit jerky on the screen there, isn't it? These individual dust grains, when they bang together, they will stick. Van der Waals forces or other electrostatic forces will make them stick together, and they will grow into pebbles, which ultimately grow into boulders, which grow into huge kilometer-sized objects that eventually grow into planets. So there's this sequence, a virtually continuous sequence from dust grains all the way up to planets as different sized objects grow. The mechanisms are somewhat different, and there's still some lack of understanding how some of these stages take place, but we think we've got, roughly speaking, the big picture of what's going on here. So again, on the same timescale that we saw for the star, we have a protoplanetary disk in which the material inside is starting to grow from micron size up to thousands of kilometers or tens of thousands of kilometers. Now, you must take it with a pinch of salt that I've got a space scale there underneath a time scale, because with this, as it stands, if we look at where the Earth and Jupiter are on the space scale, we would assume that if things are built from small things accumulating and accreting, producing larger objects, then that would imply that the small planets are made first, and then Jupiter and Saturn, the largest of planets, would be the last that would form. But that's actually not what happens. According to our understanding, based on a lot of simulations and a certain amount of hypothesis, we don't think it's the case that small planets were built first and then the large planets were the last to arrive, which is what you'd expect from this naive idea of accretion. So why is it not the case that the large planets were built last? It's all based on this idea of a frost line, or sometimes called a snow line, sometimes called an ice line. In other words, out to about 5 astronomical units, 5 times the distance from the Earth to the Sun, hydrogen ices are volatile and hence only exist as gas when you're closer than about 5 AU. When you're inside the frost line, you basically have a lot of gas. When you're outside the frost line, roughly speaking from Jupiter onwards, then these hydrogen ices do exist as solids. Water ice, methane, ammonia all exist as solids rather than vapor phase as they would in the left-hand side there. Bear in mind also that as well as hydrogen and helium, there are some heavier elements, but the little box on the bottom right reminds us that all of the stuff that we see on Earth, the carbon, the silicon, all of the heavy elements, the iron, etc., the phosphorus, the calcium, everything that makes us, all of that is only a tiny percentage of what's there. Most, 98% or so, of what's in the protoplanetary disk is hydrogen gas and helium gas. And that makes a difference because When you're dealing with planets on the right-hand side, beyond the frost line, they can start to accumulate solid ices very early on, and they can grow, and their gravity will then attract more ice and more gas. Whereas objects on the inside of the frost line have got essentially no ice to accumulate. They can only start collecting gas, and they will develop much later. So, in other words, if we look at how fast planets grow, size as a function of time, then it might be that an object like the Earth will grow like that. Inside the frost line, it's got relatively little material to grow, to accrete, and therefore it grows rather slowly. But any object beyond the frost line is able to pick up a lot of ices, and that will grow much more rapidly. So to start with, the dust grains, etc., will start to accumulate at similar speeds, but Jupiter will then go through this runaway phase, and after a few million years will grow very dramatically, whilst the rocky planets are still relatively small. So the frost line is very important for discriminating between what's going on with the small rocky planets and what's going on with the giant planets. So in fact, they're actually made in this sort of order: Jupiter first, then Saturn, then the ice giants, and the rocky planets will only start to form once the gas giants have been made. The gas giants will effectively stop accreting material when there's no more gas available. Remember, most of the gas will be cleared from around the prototype star after about 10 million years or so. So the gas giants and the ice giants will grow until about 10 million years, and then there's very little gas left for them to continue growing any further. So you can then ask, okay, right, so why is it that rocky planets don't do much until after the gas giants have formed? And that's part of the question, one of the many questions that are put together in terms of trying to understand the overall structure of the solar system. Because if there's very little ice inside the frost line, how come we on Earth have got so much water on our planet? If water and ices only existed beyond the frost line and we are well inside that, the water must have come from somewhere. So where did the Earth's water come from? And we think that the Earth was hit, along with all of the other inner planets, by a heavy bombardment of material that came relatively late, in the sense of late after the formation of the solar system. Not 4.6 billion years ago, but more like 4 billion years. In other words, a time delay of about 600 million years. And this has become known as the late heavy bombardment. Bombardment of stuff after the original formation of the solar system. We'd like to be able to understand what caused it, and along the way we'd like to understand why aren't all the rocky planets very similar. We might understand that Mercury is quite small because it's very close to the Sun, and a lot of material has been lost because of the radiation from the Sun. But Mars is further out than the Earth, so why is Mars so small? Why is Mars only 10% of the Earth mass? If it was made in a similar orbit to the Earth, picking up the similar amount of stuff, why didn't it end up a similar size to Earth or Venus? And also, can we understand the Kuiper belt, this large belt of icy objects beyond the orbit of Neptune, and beyond that, this Oort cloud, a huge cloud of icy material that extends all the way out to halfway to the nearest star. So any ideas we have, any hypotheses we have as to how the solar system formed, has to be able to incorporate these particular elements. If we look at clues that we have on the moon, for instance, here's a picture of the moon in which we can see Mare Imbrium. This is the large flat area in the top left. Apollo rock samples and analysis has told us that these are approximately 4 billion years old. This particular lava plain flooded at about that time, and it's fairly clear that there's a lot of cratering in some parts of the moon, and there's relatively small cratering in these lava areas, implying that whatever bombardment was making these craters, it didn't occur after this basin was formed. So we can use that to get a dating of when the moon was being pummeled by a whole load of bombardment of rocks. We can ask where they came from, and we'll see in just a moment. So any hypothesis that we have about the formation of the solar system must take into account that there was apparently quite a lot of bombardment about 4 billion years ago, which seems to indicate that there is a timing of some particular event that occurred 4 billion years ago. Some people contest this data because of the way the samples have been analysed, but this is the general thinking at the moment. So it means that although that's the overall picture of what we think happened, there were at least two events that were majorly disruptive to the formation of the solar system. One was called the Grand Tack, and the other is the Nice model, or at least that's not the Nice model, that's the Nice model, a model set up by the University of Nice. So there were two things happening: disruption to the inner solar system that occurred because of changes to Jupiter and Saturn's orbits, and the Nice model, 600 million years later, is an indication of what we think happened that involved changes to the outer solar system. So again, these are all just hypotheses that are put together with simulations to try and allow us to understand how we end up with the solar system that we see today. So firstly, we'll look at the Grand Tack. The Grand Tack is the idea that, if you're familiar with sailing, a tack is when you go into the wind and then back again. So in other words, a change of direction. And we think Jupiter and Saturn have changed the size of their orbits. It's a somewhat complex interaction, but if you take a single planet with a whole load of gas and dust in a big disk, then a planet can change its position, in other words, migrate inwards towards the sun or outwards away from the sun, depending on the interaction of that planet with all of the other material in the disk. Depends on the mass of the planet, it depends on whether the disk is mainly gas or mainly dust, so it's rather complicated. But it can happen that a planet, if it interacts with all of the gas outside the orbit of the planet, it can make that planet migrate inwards. And if there's a stronger interaction between a planet and all the material inside its orbit, that can make the planet migrate outwards. So in principle, a planet's orbit might shrink or expand depending on its interaction with the rest of the gas and the dust. And that is what is thought to have happened with this Grand Tack. And this is a simulation that tries to help us understand what's going on. So here we have the orbits of Jupiter, Saturn, Uranus, and Neptune. As it stands, a long time ago, these orbits were a lot closer to the Sun than they all are now. So we'll see changes to the size of these orbits, and the color coding there indicates that anything inside the orbit of Jupiter, which is inside the frost line, these are small chunks of rock, planetesimals with very little water, essentially no water. Whereas all of the blue stuff, these are little chunks of rock, planetesimals outside the orbit of Jupiter, beyond the frost line, and so these have a whole load of ices, water as well as methane and ammonia. So the color coding is just to help us see what happens to the rocks inside and what happens to the rocks outside when Jupiter and Saturn change the size of their orbits due to this migration. So let's run the animation and see what happens. And it's so fast you can barely see what's happening, other than the orbit of Jupiter is shrinking and all of the red stuff is now getting scattered to other parts of the solar system. To start with, Jupiter migrated inwards, but now we're seeing Jupiter and Saturn are migrating outwards. And that happens so fast, we'll run it again so you can see. Keep an eye on what's going on to Jupiter. It's shrinking and scattering the red stuff to the asteroid belt, effectively. And then Saturn starts to shrink, and then both Jupiter and Saturn come outwards. That's a little bit confusing because trying to keep track of what's going on, especially when on this animation it takes place on only a few seconds, is rather awkward. So let's just remind ourselves that midway through the tack, Jupiter and Saturn are in much smaller orbits. They've come right into what we would now call the inner solar system. They've scattered a lot of the material from that inner solar system out to what we now call the asteroid belt. And in the process, it's depleted that region of the inner solar system. So let's actually see what we're left with. Jupiter and Saturn, after the Grand Tack, are now back in very large orbits. Uranus and Neptune are in such large orbits they can hardly fit into this particular diagram. But what's actually important is because Jupiter and Saturn have gone into the inner solar system and then out again, they've actually basically depleted all of the rocks, all of the ice, all of the material that was in the inner solar system. All of that relatively dry material has been depleted so that when the rocky planets form, there's still enough there to make Mercury, Venus, and Earth, but there's very little left just at that point to make Mars, because Jupiter has effectively disrupted it by coming into where roughly the orbit of Mars is now. So if we look at it step by step so we can see it just a little more clearly, here we've got still good differentiation, red in the middle, blue in the outer, but basically as time goes by over many hundreds of thousands of years, Jupiter migrates inwards and starts to disrupt the inner solar system. Saturn is somewhat lighter, and so yes, Saturn will start to migrate as well, but lighter objects tend to move faster in terms of migration. So although it took a while for Jupiter's orbit to shrink, Saturn's orbit migrates very quickly inwards, and Saturn very quickly joins Jupiter very close in the inner solar system. And Saturn effectively puts the brakes on Jupiter. Jupiter migrated inwards because there was a whole load of gas outside its orbit. But now Saturn has hoovered up a lot of that material by coming in on the outside, and now it's removed that gas, which means Jupiter now migrates back outwards again. So after Saturn stops Jupiter changing its orbit, they both, as a pair, start migrating back outwards. And again, start scattering all of the rocks, all of the slightly wetter rocks as well as the dry rocks. All of this material is being scattered for a second time as Jupiter and Saturn move back out into the outer part of the solar system. And at that point, after a few 100,000 years, the grand tack finishes. So this is speculation, this is hypothesis, but it has the advantage that it explains why the asteroid belt is full of some material which appears free of water, but some material that has water. In other words, it's mixed up stuff that used to be inside and outside the frost line, and it explains why Mars is a relatively small planet. So the grand tack, not universally accepted, but a number of people think the grand tack is the possible explanation for a number of different features within the solar system, explicitly what's going on in the inner solar system, the asteroid belt, and what happened to Mars. And it looks like we have to have something completely separate to understand things like what the outer solar system is doing and why it looks the way it does, and why we ended up with so much water on the Earth. And that's a whole series of simulations based on calculations carried out at the University of Nice and elsewhere, which has now become known as the Nice model. So although the grand tack is effectively what Jupiter and Saturn did to disrupt the inner solar system, the Nice model is what's going on in the outer solar system and how that changes. So here we've got, forget the inner solar system, that's now all relatively stable and the planets have formed and they're not going to do anything. But here we've got what's happening with Jupiter, Saturn, Uranus and Neptune, and outside the orbit of Neptune we have a large dense disk, a huge number of icy rocky particles that's left over from the protoplanetary disk. If that was still what we thought was there in the early solar system, we would see a huge number of objects beyond Neptune, whereas in fact, apart from Pluto and a few other small objects, we don't see many objects beyond the orbit of Neptune. So what that disk is like then has certainly changed in the intervening time. And we think this happened on a timescale of hundreds of millions of years. And again, a simulation tells us what do we think happened. The simulation I'm about to show, again, it only lasts a few seconds, but what happens is Jupiter, Saturn, Uranus and Neptune will all change slightly. We tend to think of orbits of planets as being stable, but on timescales of hundreds of millions of years, they aren't. They're going to change slightly because of this idea of migration inwards or outwards. But at some key point, it is thought that the period of Jupiter, which is currently about 10 years to go round the Sun, and the period of Saturn, which is currently about 30 years to go round the Sun, at some point in history, about 500 million years after the solar system formed, we think what happened was that Jupiter and Saturn got into resonance. In other words, a certain number of orbits of Jupiter were exactly an integer ratio of a certain number of orbits of Saturn. It might be that 2 orbits of Jupiter was 1 orbit of Saturn, or possibly 2 to 3. It's a ratio of 1 to 2 or 2 to 3. People disagree as to what the resonance actually was, but most people agree there was a resonance between Jupiter and Saturn, and as soon as 2 planets get into resonance, they start to tug on each other and everything else in the vicinity, and basically everything goes to pot. So let's actually see that animation run. So again, we've got a few green objects on the outside. Jupiter, Saturn, Uranus and Neptune look quite happy where they are. And indeed, that happens. But for a suddenly, kablooey, you get Jupiter and Saturn in resonance, and there is a sudden change in the orbits of everything in the outer solar system. And Uranus and Neptune have now moved to the outer part of the solar system, and in the process, they have effectively completely depleted all of the material that was all of those green dots that we saw before, because the planets have now been bulldozing their way through this region. All of those little rocks, all of those little planetesimals that were there have now been scattered. And we think a lot of them are scattered into the inner solar system. That's why there was a late heavy bombardment some 4 billion years ago. That scattering of Uranus and Neptune changing their positions because of what Jupiter and Saturn were doing, that's produced a whole load of rocks carrying water coming into the inner solar system, hitting the moon, producing the craters, hitting the Earth, producing our oceans. It also will have scattered a whole load of material out, further out than this, beyond many tens of astronomical units from the Sun, and that will have effectively populated a rather sparse Kuiper belt going out quite some considerable distance, and also ultimately would have scattered, because the scattering wouldn't necessarily send them out in the plane of the ecliptic, in the plane of the Earth's orbit. It would have scattered them out into the large spherical Oort cloud that surrounds the Sun at huge distances, a fraction of a light year away from the Sun. So it is generally thought that although we can get a pretty good idea of what's going on by looking at other stars and seeing how stars developed, and we now have the ability to use telescopes like ALMA to actually see protoplanetary disks around other planets, understanding why we have this particular collection of gas giants and rocky, and why is it this and why is it that, is based on the hypothesis that there's been these two rather disruptive events, Jupiter and Saturn changing their orbits, the so-called grand tack, basically disrupting the inner solar system, and then this Nice model, which is responsible for producing the Kuiper belt and producing the Oort cloud, as well as producing the late heavy bombardment, which gives us a whole load of water coming in to the inner solar system. So a lot of hypothesis, because we don't always have the facts. We know what the solar system looks like now, and we have to make hypotheses and set up models and run simulations to see if our understanding of how things have changed in the past can possibly lead to the solar system that we see today. And of course, the more exoplanet systems that we study, the more solar systems around other stars, the closer we get to understanding whether this sort of modeling is indeed a sensible way to understand the way our solar system came into being. Thank you very much.